Let's start with reviewing the energy principle. And this comes from a few chapters ago when we thought about conservation of energy. We have an object which has mechanical energy, such as its kinetic energy and its potential energy of a variety of sorts. We then have the microscopic energy, which is the thermal energy. And we know that this is going to relate to temperature. We had two different ways of writing the conservation of energy idea in variables. One was that the changes of each of them summed together equals the external work, or we can say that the change in our total system energy is equal to external work, where we can then break up the change in system energy to be the change in mechanical energy, which is just change in K plus change in U, plus the change in thermal energy. So when we met this, we called it the basic energy model. And at the time, we noted that we were going to make it a little more complicated when we got to thermodynamics, and the time is now. Let's review, before we go on, how we used some bar chart diagrams to think about this. And part of this is also going to be reviewing work, because work is going to be really important for what we talk about next. So initially I have a block and it has some kinetic energy because it's moving. And I'm now actually lifting it at steady speed. Now, if it's being lifted at steady speed, that means that my velocity is not changing. Well, if the velocity is not changing, my kinetic energy initial and final are the same. But I've done work. Remember that work can be expressed as force integrated over a distance. So I've done some work while lifting it, but that has just become my potential energy. If I consider my initial moment, my initial position, and my final position, that final position has potential energy, even if I define this initial position to have zero potential energy. Now in this system, we didn't say that there was friction anywhere or air resistance, so we didn't think about a change in thermal energy. However, we can turn this block on its side and put it on a surface, and now pull it along the surface, again at a steady speed. Now again, if it travels a given distance, even the same distance, we then have the same initial and final kinetic energies, but now no change in potential energy, no potential energy at all. We still have work done, and this is an external work because this is tension. We can't define tension to be any sort of potential energy. It must be an external force to our system if the system is still, say, the block and the surface. So we've still done work, same amount if it was the same tension over the same distance, but now we would say that that work all became thermal energy. So this is friction, really. So this should make sense. We've seen that we can do work on the system, turn that into a mechanical energy, and or turn that into a thermal energy. You could imagine in either of these situations, I could have actually increased my tension, which would have increased my work. And in this case, that would have turned it into more kinetic energy. And in this case, it also would have turned it into kinetic energy in addition to the thermal energy. So work becomes a final energy increase over your initial and or a change in your thermal energy. But what is this missing? Imagine that I take a pan of water and I put it on the stove so that it's being heated. I see that the temperature of that water is increasing, or I put my hand in it and I know it happens. So clearly I have a change in thermal energy, which relates to temperature. The temperature has increased, the thermal energy has increased. I know those little water molecules are bouncing around more. But I haven't done any work on the system, if I consider the system to be the pan of water, and I haven't changed the mechanical energy at all. So where did that come from? Similarly, I can take a banana and I can put it in the freezer for making banana bread later. And in this case, that banana is going to get cold. That thermal energy is going to decrease. But I haven't done any work on the system. Again, if we imagine the initial state being the banana right outside of the freezer at the same height. And we also haven't changed the mechanical energy of the banana. It was initially at rest and it's still at rest, but it's now colder. So we know that if we want to talk about thermal energy being related to temperature, we have to account for these situations that are thermal interactions, which are transferring energy in the form of heat, where either we have made our system increase in temperature or decrease in temperature. So we say that we've either transferred heat into our system or away from our system. But this clearly is different from what we've been talking about so far. So we have a new energy model where our change in energy of the system, where this is the mechanical energy and the thermal energy, is equal to the work done, where we're dropping the external work, because when we talk about thermodynamics, external work is the only type of work we ever mean. So this is now external work plus Q, where Q is heat. And in general, what we should be writing is just Q, not delta Q, though I do occasionally make a mistake there. Similarly, we should always be writing W, not delta W. And part of that is that energy is a state variable, so you can have a change. Work and heat are not state variables, so you can't technically have a change. These are transfers of energy from one system into another. Work is kind of in a mechanical form, the forces that we already know about, and Q is heat. This is a thermal interaction. So now, moving forward in thermodynamics, we're going to be talking about these variables in more detail and understanding how these relate to our ideal gas processes.